Hi everyone, welcome to EE140 practice problem. So for this problem, a long thin non-conducting rod carrying a non-uniform charge density lambda is placed on a ground plane, and our goal is to find the electric field at the point E and also to find the surface charge density at that same location. So the distance r away, it's right here. We'll draw it from the rod as big R, and the effects from the rod, since it's a positive charged rod, will be towards that point. We'll just pick a small point, which will this. And assuming this is an infinite plane, the best way to approach this problem would also be to draw another rod on the opposite end, but with the opposite charges, so negative in this case. And from here, the DE negative will be towards the rod. This will be DE negative, and this will be DE positive. And the net of these two will be just going straight down in the Z direction. Okay, so this is what we have to find. So first, we'll use this equation right here, 1, to find the electric field, and equation 2 will be to find the surface charge density. Let's start with 1. So our dq is what we also don't know at the moment, so let's do that first. dq will be the charge density, which is given to us right here, lambda, times a small dz. Since we know our dq now, we will write another equation, which is going to be dez, since that's the direction we have to find our electric field. The equation will be, since in the negative direction, it's in the negative z direction, it's going to be negative dE, which is the equation above right here, and sine theta. The reason I got sine theta is because if I draw a right triangle, the angle sine theta will give me the z part of it, which is exactly what I need. From there, I subbed everything in, and this is the equation I got. Now, having that equation, we'll take the integral from 0 to infinity, and we'll come down right here. There is still negative k lambda out here, but we'll take care of that at the end. So from there, what I did is I showed the r as respect to z and big R, and that's just using Pythagorean theorem, which is going to be r squared equals z squared plus big R squared. With that, I plugged the r squared in there, giving me this integral. At this point, we have to do u sub to solve this integral, and the u I took as z squared plus r squared dz. From doing the u sub, you will result to this integral, and then I finally took the integral with respect to du, giving me this, with my limits being infinity to 0. And once plugging those in, you will result with 1 over r. And now you'll just combine everything together, giving you E total. And remember, we have to bring in the negative 1k lambda back in here, and it's going to be negative z hat direction 2k lambda r. And K can also be represented as 1 over 4 pi epsilon naught, which is exactly what I did, giving me a final answer of negative z hat lambda divided by 2 pi epsilon big R. So now we know our electric field, and the next part of it is to find the surface charge density, which we'll use this equation. Coming down here, this is the equation. This equation can also be written as this right here, where it's epsilon naught EZ1 above the ground and epsilon naught EZ2, which is below the ground. Since there is no actual field underneath the ground, we will consider this to be 0. And then for EZ1, we will plug in the value that we just got, and the epsilon naughts will cancel out, giving me a final answer of negative lambda over 2 pi big R as my surface charge density.